Right? So let's continue. We'll have to repeat some of the important history of operating system because it is such an important topic. So the desire to support multi-programming and overlap in the presence of I input and output and interrupts force innovation in the conceptual development of operating systems along a number of directions. Issues such as memory protection became important. We wouldn't want one program to be able to access the memory of another program. Understanding how to deal with the concurrency issues introduced by multi-programming was also critical, making sure the OS was behaving correctly despite the presence of interrupts. So we wouldn't want program to be able to access the memory of another program. That's why we have this virtual memory. And understanding how to deal with the concurrency issues introduced by multi-programming was also critical. So the issues of multi-programming which leads us to the creation of different process to stop one at a time because in a way that's also how we conduct our task. We only conduct it per process. We can only focus one at a time. So this is not as hard as people might think because it mimics how we naturally think. Making sure the OS behaving correctly despite the presence of interrupts is a great challenge. We will study these issues and related topics later in the course. One of the major practical advances of the time was the introduction of the Unix operating system, primarily thanks to Ken Thompson and Dennis Ritchie at Bell Labs, yes, the phone company. Unix took many good ideas from different operating systems, particularly from Multics, and some from systems like 10X and the Berkeley Time. Sharing system, but made them simpler and easier to use. So this is how the sharing of programs or command was born. Soon this team was shipping tapes containing Unix source code to people around the world, many of whom then got involved and added to the system themselves. Underlying the original Bell Labs, Unix was the unifying principle of building small, powerful programs that could be connected together to form larger workflows. So this small program connected together to form larger workflows. And again, just like in interaction design, this workflow or patterns allow us to uh, cognitive cognitively put our thinking to the computer. It's like a cognitive annotating where we put or cognitive tracing where it allows us to offload our cognitive task to outside world. So that's what what this workflow does. So the shell, where you type commands, provided primitives such as pipes to enable such meta-level programming. And thus, it became easy to string together programs to accomplish a bigger task. Again, to string together these little files to form a bigger task. For example, to find lines of a text file that have the word foo in them and then count how many such lines exist, you would type grep foo file.txt and then vertical line wc -l, thus using the grep and wc word count programs to achieve your task. Also of critical importance was the accessibility and readability of the code. Having a beautiful small kernel written in C invited others to play with the kernel, adding new and cool features. For example, an enterprising group at Berkeley, led by Bill Joy, made a wonderful distribution, the Berkeley System Distribution, or BSD. So earlier, as I said in the about design course, is that this is how we create an icon or a combination of GUI, such as idiom, is used to be a command line program. So this used to be it. So at that time, this was an actual innovation because it allows you to program in meta level. It allows you to pipe commands or string these commands together to produce a more powerful result. So, a critical importance as well was the accessibility and readability of the code, because the more readable it is to others, the easier for them to string it and to create a more powerful system. Remember, the more code we have, the more complicated it has, the more difficult it is to use. So, the accessibility and simplicity of this code allows for more developers to contribute to make it even more efficient. So, having a beautiful small kernel written in C invited others to play with the kernel. So, this kernel or operating system or Unix was actually written in C. So, this simplicity allow others to add new and cool features. For example, an enterprising group at Berkeley led by Bill Joy made a wonderful distribution, the Berkeley Systems Distribution, which had some advanced virtual memory, file systems, and networking systems. Joy later co-founded in Microsystems. So again, it's still trying to improve the basic principles of computer, which is the network, the virtual memory, and the file system. So Sun Microsystem was born from that. Unfortunately for operating systems, the PC at first represented a great leap backwards, as early systems forgot or never knew of the lessons learned in the era of mini computers. For example, early operating systems such as DOS, the disk operating system from Microsoft, didn't think memory protection was important. Thus, a malicious or perhaps just a poorly programmed application could scribble all over memory. The first generation of the Mac OS, V9 and earlier, took a cooperative approach to job scheduling. Thus, a thread that accidentally got stuck in an infinite loop could take over entire system, forcing a reboot. So unfortunately, sometime before, this operating system did not fully learn from the past. So there's a lot of viruses, and this thread that accidentally got stuck in an infinite loop could take over the entire system. So it didn't apply the software engineering principle of modularity and security. The painful list of OS features missing in this generation of system is long, too long, too long for a full discussion here. So a lot of list of the features that are modern operating system today was too long that existed now to discuss in this history. Fortunately, after some years of suffering, the old features of mini computer operating system started to find their way onto the desktop. For example, Mac OS or Mac OS has Unix at its core, including all of the features one would expect from such a mature system. So the Mac OS actually has Unix at its core. So again, it all stemmed from Unix. Windows has similarly adopted many of the great ideas in computing history, starting in particular with Windows NT, a great leap forward in Microsoft OS technology. Even today, cell phones run operating systems such as Linux that are much more like what a mini computer ran in the 1970s than what a PC ran in the 1980s, thank goodness. So we actually mimic the principles in 1970s done in what 1980s. Additionally, Facebook, Google run Linux because to avoid legal complications, because Linux is an open source system, but Linux is a complete overhaul of Unix. It has a different syntaxes. That's why sometimes it's hard to learn compared to well written Linux or Unix. It is good to see that good ideas developed in the heyday of OS development have found their way into the modern world. Even better is that these ideas continues to develop, providing more features and making modern system even better for users and applications. Unfortunately, due to time constraints, there are a number of parts of the OS we won't cover in the book. For example, there are a lot of networking code in the operating system. We leave it to you to take the networking class to learn more about that. Similarly, graphics devices, particularly important to take graphics course to expand your knowledge in that direction. Finally, some operating systems book talk a great deal about security. We will do so in the sense that OS must provide protection between running program and give users the ability to protect their files. But we won't delve deeper into security issues that one might find in a security course. However, there are many important topics that we will cover, including the basics of virtualization of the CPU and memory, concurrency, and persistence via devices and file system. So we will discuss how the persistence in disk, the memory, the concurrency, and the security in such a way that we protect files between different applications, but not to the point that we will gonna discuss a deep level security, kind of like in CompTIA Security Plus. Additionally with this is that we're trying to learn the millions of code of operating system. So we're trying to learn an entire application here. You can think of this as just a software. So we're gonna try to learn each of its syntax and characteristics. So let's start. So virtualization. In this chapter, we discuss one of the most fundamental abstraction that the OS provides to users, the process. The definition of process informally is quite simple. It is a running program. The program itself is a lifeless thing. It's just sit there on the disk, a bunch of instruction, and maybe some static data waiting to spring into action. It is the operating system that takes these bytes and gets them running, transforming the program into something useful. So before I mentioned that CPU is the one that transfer the data from disk to memory, but actually it's the OS and it's deeper than that. So we will discuss that further here. A program just sit on the disk with a bunch of instruction and some static data, such as the variables that the function initiate, waiting to spring into action. It turns out that one often wants to run more than one program at once. For example, consider your desktop or laptop where you might like to run a web browser, mail program, a game, a music player, and so forth. In fact, a typical system may be seemingly running tens or even hundreds of processes at the same time. Doing so makes the system easy to use, as one never need to be concerned with whether a CPU is available. One simply runs programs. So, since the first operating system is just a library of API, it's just a library before. Now, an operating system is more than that. It needs to accommodate more programs because one, like our attention, our memory, we discussed in the previous video, we can only, though we focus on one at a task, we do a lot of tasks in our head, right? So that's the same with program. We also run different programs related to our task. Doing so makes the same easy to use, as one never need to be concerned with whether a CPU is available. One simply run programs. Now, with all the available hardware to us, such as CPU, memory, uh, disk, network, how are we able to use the operating system to juggle to these multiple tasks? So that's where the concurrency concept came from. So the OS creates this illusion by virtualizing the CPU. By running one process, then stopping it, and running another, and so forth. The OS can promote the illusion of that many virtual CPUs exist when in fact there is only one physical CPU for a few. The basic technique known as time sharing of the CPU allow users to run as many concurrent processes as they would like. The potential cost is performance, as each will run more slowly if the CPU must be shared. So the way an operating does this in a high level is time sharing. Later we will discuss the details on how it actually does separate these processes. To implement virtualization of the CPU and to implement it well, the OS will need both some low-level machinery and some high-level intelligence. We call the low-level machinery mechanisms. Mechanisms are low-level methods or protocols that implement a needed piece of functionality. So, a mechanisms, kind of like the hardware modules, the trap, are the low-level methods or protocols that implement a needed piece of functionality. So again, it's functionality. We would not call that functionality if that pieces of hardware or mechanism or low level of methods or protocols. So we wouldn't work hard to do that if that functionality is needed. Because again, as we learned in the previous video, functionality is a needed thing, right? For example, we learn how to implement a context switch, which gives the OS the ability to stop running one program and start running another on a given CPU. This time sharing mechanism is employed by all modern OS. So again, it goes back to the memory. Though we have one attention span or attention task at a time, we can switch to that. However, we need to stop the other, right? Because we have limited memory. One of these mechanisms resides some of the intelligence in the OS in the form of policies. So another thing is that since these mechanisms are low level, the mechanism for high level are called policies, or the way we manage this high level. Like what I've said in the previously, policies answer which program runs first and which based on the policy. So policies are actually algorithm, like we discussed in the previous video, for making some kind of decision within the OS. For example, given a number of possible programs to run on a CPU, which program should the OS run? A scheduling policy in the OS will make this decision, likely using historical information. So again, this is the keyword policy, historical information. Also with our design, right? We check which program has run more over that last minute, or in design, what is the previous settings of that window. We need to go back to that, because as we know, people only use this few things at a time, right? Kind of like doing a toothbrush. Workload knowledge. Oh, it's also the workload knowledge, the domain of the person using it. Kind of like in modern applications with idiom that has needs a context with what they're doing. What types of programs are run? So it also depends on the programs. Again, it's related to the domain or the users as well, whether it's beginner, intermediate, or expert. And performance metrics. Is the system optimizing for interactive performance or throughput to make its decision? So those are programmed in details. So that's also what makes the OS today um, make this nuance transformation, because it allows us to meta program using this few simple steps such as clicking or command reading all these um, files. Now it's actually an AI, right? So the abstraction, the process, uh, the abstraction provided by the OS of a running program is that is something we will call a process. So a process is actually a key in virtualizing the CPU, memory, and disk. So, and we will call this a process. As we said above, a process is simply a running program. At any instance in time, we can summarize a process by taking an inventory of different pieces of the system it accesses or affects during the course of its execution. So, a process again is, in its simple definition, uh, is just a running program at any instance in time. So the time or the state in time also affects how we describe it. And we can summarize the process by taking an inventory of different pieces of the system it accesses or affects during the course of its execution. So we're tracking it as well using the PCB, right? Using the OS as well. So the way we track this is actually through PCB, which we're gonna later discuss. But as you can see, the system it accesses or affects during the course of its execution. So let's say I'm taking a note now in OneNote. So this is a kind of process that is running now on my operating system because I need to do something. I need to take note. I need to present. Now, this is what you call process. You will only call that process if it's actually been used. If not, it's called a program because it's just stuck on bytes. It's just stuck on your disk. It haven't been used. To understand what constitutes a process, we just have to understand its machine state. What can read? We need to understand the machine state. What can program can read or update when it is running. So it's also we're understanding the function. It's it kind of like different file or code are different or different algorithm are different because they achieve different things or different transformation at any given time. So at any given time, what parts of the machine are important to the execution of the program? What variables? What is it trying to do with respect to the user? Is it needed by the user or is it not? So one obvious component of machine state that comprises one obvious component of machine state that comprises a process is its memory. Instructions lies in memory. So one of the components of that machine state by the process is its memory, the instructions that lie in memory, the instruction that your program put or attempt the memory to process. The data that running program needs, reads and writes sit in memory as well. So the data that the running program reads and writes sits in memory as well. So the data that you have in disk was actually copied to the memory where the process reads and writes it. Thus the memory that the process can address, called its address space, is part of the process. So that's the memory where you copy that from CPU, the instructions and static variables, and where you write and read it is actually called an address space. Also part of the address of the process machine state are registers. So another part of this machine states are registers. So again, process in its simplest form is just a running program at any instant in time. We can summarize process by taking an inventory of the different pieces of system it accesses or affects during the course of its execution. So to understand what constitutes a process, we just have to understand its machine state, what a program can read or write when it's running at any given time, what parts of machine are important to execution of this program. So what might seem simple as process actually is a complicated one because it has a different component, just like this machine state. We're just not talking about the uh, system we access or it affects during the course of execution, but also what constitute that process. What program can read or write and update, because again a process is like a code, it's different in different scenarios. So how can we provide a description that allow us to understand this process? So that's one of our first question for us to understand what how the OS actually virtualize the disk memory and networking and CPU to make the system easy to use and to make the system easy to use, make it powerful, and at the same time serve its user goals. So one component of that machine state that comprises a process is its memory. So instructions lie in memory. The data that's running program reads and writes sits in memory as well. Thus, the memory that process can address, called its address space, is part of the process. Also part of the process machine state are registers. Another thing is aside from instruction is the registers. Many instructions explicitly read or update registers. So what are registers? It's highly connected to instructions. So it's explicitly read or update the registers and thus clearly are important to the execution of the process. So why registers matter to a process? When it says part of the process machine states are registers, it means a process isn't just a code plus memory. It also needs to remember what the CPU was holding at that exact moment, like which instruction it was about to run, program counter register. So which instruction in that code that you copy from disk is about to run, what values it was working on. So what values that instruction working on, general purpose like EAX, EBX, ETX, and x86. What flags or condition, bits or set, status registers. As you can see, there's a lot of different transformation that you have to define. When the OS switches from one process to another, it must save all those registers and then restore another process registers. So it must if you switch or stop another one, you should save all these registers. So these instructions instruction that explicitly read or write update the register must stop, since the OS will switch program. It must save all those registers and then restore another process registers. Otherwise, both processes would override each other's hands-on work. Again, otherwise, both processes would override each other's hands-on work. So if you do not apply this concurrency, the processes would actually override the other's work. It's kind of like in Google Docs, where anyone could edit the file at the same time. So you must be careful of that because you may have a problem in synchronization because everyone could make transformation at any given time. Analogy, so think of RAM as your whole desk with documents, books, and tools. Registers are the pen in your hand plus the line you are currently writing on. If your manager, the OS, tells you to stop and let someone else use the desk, if your manager, the OS, tells you to stop and let someone else use the desk, you must put down your pen, mark your page, and step aside. When you come back, you want your pen and page exactly as you left them. So when you switch process, you want your pen and page exactly as you left them. So you want instruction to read or update that register exactly as you left them. That's exactly what the OS does with registers during a context switch. So we will refine this notion further as we get into more and more detail. But that's what you call context switch. Now, note that there are some particularly special registers that form part of this machine state. For example, the program counter, sometimes called the instruction pointer or IP, tells us which instruction of the program will execute next. So there is value or properties of this or type of these registers are special, such as this program counter, sometimes called the instruction pointer or IP, which tell us which instruction of the program will execute next. It's kind of like pointer to the next instruction. So the instruction update or read this register, but sum this register actually is the key for you to be able to get to that next to execute that next instruction. I think it's kind of like node data structures. Some you need the linked list. I think just need to be connected to the first one in sequence to be able to connect to the next node, and subsequently to the third node, fourth node, fifth node, etc. So similarly, a stack pointer is a special as well, and associated frame pointer are used to manage the stack for function parameters. So a stack pointer, which we will see later, that change the virtual memory of that current process with respect to the function parameters, local variables, and return addresses. So this is how the code runs in the memory in details. We actually need this stack pointer, or what we call SP, and associated frame pointer to return to and return addresses once our process has exited and killed. So the desire to support, sorry, we just repeated this. So though we defer discussion of a real process API until a subsequent chapter, here we first give some idea of what must be included in any interface of an operating systems. These APIs in some form are available on any modern operating system. So at some form, these API are the basics that are available in some form in modern operating system. It does not need to be exactly the same term, but you get the idea. These are the basic APIs. So create an operating system must include some method to create a new processes. So this method is like an API or a system call that allows the operating system to create that new process. So this is what we will gonna use in our code. So when you type in command into the shell or double click on an application icon, the OS is invoked to create a new process to run the program you have indicated. So when you actually type a command or double click an icon, in reality, what you're doing is creating a new process for that, or you're invoking this create API to the operating system. You're not invoking this to the program because again, a program is just a data seated in the disk. So for that to come alive, The process is actually what makes that happen. So destroy, as there is an interface per process creation, systems also provide an interface to destroy processes forcefully. Of course, many processes will run and just exit by themselves when complete. When they don't, however, the user may wish to kill them, and thus an interface to halt runaway process is quite useful. So a destroy, if in control shift escape, as you can see, guys, in this modern GUI system, we don't actually see this code because it has been abstracted to us in great details, actually, with OS, with program, and now in idioms in GUI. That's why with a simple control shift escape and then deleting that, what you're actually doing in the background is invoking this destroy API of the operating system. Now wait, sometimes it's useful to wait for a process to stop running. Thus some kind of waiting interface is often provided. Miscellaneous control, other than killing or waiting for a process, there are sometimes other controls that are possible. For example, most operating systems provide some kind of method to suspend the process, stop it from running for a while, and then resume it, continue it running. So wait, sometimes it's useful for a parent to wait for its child to stop running. Thus, some kind of waiting interface is often provided, for the process to say it's complete, because some functions or some things that we do needs to be waited, such as downloading, etc. Miscellaneous control, other than killing or waiting for a process, there are sometimes other controls that are possible. For example, most operating systems provide some kind of method to suspend a process, stop it from running for a while, and then resume it, continue it running. So this is one of the basic API for the operating system with regards to its running program or process living in memory. There must be some kind to stop it and then resume it. This is actually at the heart of the concurrency. Status. There are usually interfaces to get status information about process as well, such as how long it has run for or what state it is in. So remember, an operating system is used to manage programs securely, efficiently, and make this running of a program that used to be complicated with one person or one computer scientist doing all the work of a program is now abstracted to us by an operating system. So it must be, it has some way to track it using PCB, which we're gonna discuss later. All the process must be tracked, so it must have some data structures as well. So again, it's a software, just like the data structures and algorithm and the applications we've been discussing before. It's also a software that needs to be to have a data structures and algorithm under the hood. So here's loading from program to process, a simple diagram, but we will gonna refine this as we move forward. Now this, you have code and static data in the program. Now loading means takes on this program and reads it into the address space of address. So an OS actually create this memory or allocate that memory, and then takes on this disk program and reads it into its address space. So this is what an OS does. As you can see, there's a CPU or are connected. So the first thing that the OS must do to run a program is to load its code and any static data, initialize variables into memory, initialize variables. So this is the function parameters, the registers, along with this process memory state and instruction that needs to load into the memory, into the address space of the process as well. So programs initially reside on disk in some kind of executable format. The process of loading a program and static data into memory requires the OS to read those bytes from disk and place them in memory somewhere. So this process in its basic form is again an OS taking these bytes and reading those disks in some memory somewhere, because that's the basic of computers. You need to read it in memory to make it come alive. So in early or simple operating system, the loading process is done eagerly all at once before running the program. So as you can see before, at the start, it loads all the program before making the process comes alive. But today, you allocate first, and then modern OS perform the process lazily by loading pieces of code or data only as they are needed during the program execution. So now it's only process or taking load. It is loading it as it goes, as they are needed during the program execution. To truly understand how lazy loading of pieces of code and data works, you'll have to understand more about machinery of paging and swapping. So this is where we start getting confused, because these details are actually is the topic of the next videos. But in high level, this is how it works. You have a program in disk, the OS transfer that into the memory, but that process that seems to be before, that before is all at once, which now using a lazy loading, one at a time, needs an understanding of the machinery of paging and swapping. So topics we'll cover in the future, but essentially those are the part of the OS and the memory on how it manages this program process memory. When we discuss the virtualization virtualization of memory. So it's all about the virtualization of memory. That's what's making it complicated. But for now, it suffices to understand that those code are being taken somewhere in the virtual memory to make it come alive. So for now, just remember that before running anything, the OS clearly must do some work to get the important program bits from disk into memory. Once the code and the static data are loaded into the memory, there are a few other things the OS needs to do before running the process. Some memory must be allocated for the program's runtime stock or just stock. So again, once the code and static data are loaded into memory, there are a few other things the OS needs before running the process. So once it's loaded, it doesn't immediately start it. So because you allocate first, you load the program, you don't start and then get to the main. Or to start some memory must be allocated for the program's runtime stock or just stock. So some memory or part of that memory must be allocated just for the program's runtime or the stock or the execution or the sequence of execution. Stock is just a last in, first out. So you should as you should likely already know, C programs use the stock for local variables, function parameters, and return address. So aside from loading that program, taking up some memory or allocating some memory for that program instructions and data, there is another or part of memory that also took care of that program's local variables, function parameters, and return addresses, so that the OS know when the program has exited. So the OS allocates this memory and gives it to the process as well. The OS will also likely initialize the stock with arguments. So the OS also initializes that with arguments. Specifically, it will fill in the parameters to the main function like arg and argv-array. So this part of this memory will actually be initialized by the OS So this stack will actually initialize with an arguments. It will fill in the parameters to the main function to start the program. So that's the memory, part of the memory, and OS will actually the one that will allow this or invoke this main using this argc and argv-array. So this main function are used to start the program itself. So that's the start of the program. But we will further refine this concept as we move. So the OS may also allocate some memory for the program's heap. In C programs, the heap is used for explicitly requesting dynamically allocated data. So aside from stock, the depending on the program, it may also allocate some memory for the program's heap. So again, the program stack and the program heap. If the program are using heap, in C program, the heap is used for explicitly requested dynamically allocated data. So a program explicitly requested for dynamically allocated data. So those data are actually changing. Those allocated program requests such space by calling malloc and free it explicitly by calling free. So see, the reason it's dynamic is because this program allocate using malloc and freeing it during that process using free. So the heap is needed for data structures such as linked list, hash tables, trees, and other interesting data structures. So as we have discussed, these are great for queue task, right? The heap. So the heap will be small at first as the program runs and requests more memory via the malloc library API. So malloc is actually an API or system called this program use to invoke to the OS. So this actually are calling API. The OS may get involved and allocate more memory to the process to help satisfy such calls. So the OS now will allocate memory to this call of the program. So as we notice, the reason it grows is because it's a dynamic data, allocated data. Also, as we have discussed in the previously, we need to we are trying to minimize or optimize the time complexity and the space complexity. That's why we're using this data structure. That's why program are using those kinds of data structure. Now, by loading the code and static data into memory, by creating and initializing a stock. So again, by loading the code and static data into memory, by creating and initializing a stock. So you load the code and data into that virtual memory and also allocating a memory for a stock, and by doing other works as related to input and our output setup. So maybe you're calling malloc. The OS has now finally set the stage for program execution. So after we've done this allocation for virtual memory, not only the time the OS finally set the stage for the instruction or the algorithm to run. It thus has one last task to start the program running at the entry point, namely main. So this main is again what we mentioned earlier. One was called by the stack, right? So like the OS will also likely initialize the stack with arguments. Specifically, it will fill in the parameters to the main function. So after we've done that, this stack are actually the one that decides which to run first, and this stack in part of that virtual memory will actually invoke that main function of the program. So namely main. So by jumping to the main routine through a specialized mechanism, So again, that part of virtual memory that invoke the start of the program using system calls. So this is actually how the program uh, will actually start, or the process actually start. So you might think when you double click an icon, it's magic, but in actuality, it only invoke that actual program when this system call or API provided by the OS has been invoked. So this mean are actually an API as well. So by jumping to the main routine through a specialized mechanism that we will discuss next chapter. So this actually has an intricate details as well. Uh, the OS transfer controls of the CPU to the newly created process. So after this, through specialized mechanism, now the OS will transfer the control of the CPU from the OS to the newly created process, and thus the program begins its execution. As you can see, the OS allocates first these three memories: the stock and the data of the program, the virtual memory from the stock, the virtual memory from the dynamically allocated data such as malloc, right? So it sets this up uh, to accommodate all the security requirements, the time sharing, the policies to allow the OS before it invokes the main. So main is a system API that allows to transfer the control from trap again to the trapping the kernel to invoke the hardware to transfer control now to the program. So the OS transfer control to the CPU to the newly created process, and thus the program begins its algorithm or its execution. Now that we have some idea of what a process is, though we will continue to refine this notion and roughly how it is created, let us talk about the different states a process can be at a given time. So the notion that a process can be in one of these states arose in early computer system. In simplified view, a process can be in one of these three states. So in simplified view, this is the first concepts in early computing system. So running in the running state. A process is running on a processor. This means it's executing its functions. So once we invoke that main, this is the state that we are in. We're actually running the state. Um, in the running state, a process is running on a processor now because the CPU always transfer that to the process, the control to that process. But later it will return its return interrupt to transfer back the control of this process to user mode. This means it's executing instructions. So in this running state on main, it means it's executing functions or instructions on the CPU. So it's now having your CPU do something. So this is the function you want to do. Ready, in the ready state, a process is ready to run, but for some reasons, the OS has chosen not to run it at this given moment. So there is also a ready state, which means that it is not executing instruction to the CPU, but it's ready to do so. So it is done so, such as the program you don't currently use, because you only use one at a time, again because of the principle of your memory, right? You can only do one at a time. So that's kind of like the policy or principles running on this by the OS as well. So block, in the block state, a process has performed some kind of operations that make it not ready to run until some other event takes place. So this process of block is actually now doing something such as an input or output or waiting for a packet. A common example, when a process initiate an IO request to the tick, this it becomes blocked, and thus some other process can use the processor. So it's not using processor, kind of like in disk, it's a different software that our file system are actually the one communicating to the disk. So it's not actually talking to the processor. So it's like saving something on the file or like waiting for the packet. This process could be on that block state as well. But there's many state as well once that main has been invoked on the process. So the OS is now has control on this process. So if we were to map these states to a graph, we would arrive at the diagram in figure 4.2. As you would can see in the diagram, a process can be moved between the ready and running state at the discretion of the OS. Being moved from ready to running means the process has been scheduled. So this is also how the policy schedule it, or the scheduler schedule the process from moving from running to from ready to running. As you can see here, it was scheduled, and from running to ready, it's the scheduled. So this the main concept. This is also how we run concurrency. How we transfer program to one program that we focus, such as me in OneNote, and then when I go to Chrome, the processor transfer that to another process. So this is actually how it does just at its scheduled and descheduled it in a high level, of course. So being moved from ready to running means the process has been scheduled. Being moved from running to ready means that the process has been descheduled. Once a process has become blocked, like by initiating an I/O operation, the OS will keep it as such until some event occurs, like I/O completion. So that's the missing keyword here, until some event occurs. So there's a rules for that as well by the OS, which makes this amazing software, right? So at that point, the process moves to the ready state again and potentially immediately to running again if the OS so decides. So here's an example. In this next example, the first process issues an I/O. So first, it's issue an I/O. So it's initiate an I/O here. Running. So it became blocked. After running some time, at that point the process is blocked, giving the other process a chance to run. So now the other process is kind of like when you're using OneNote and then you move, the other process is now using the processor. Giving the other process chance. So figure 4.4 shows a trace of this scenario. More specifically, process 0 initiates an I/O and becomes blocked, waiting for it to complete. Processes becomes blocked, for example, where when reading from a disk or waiting a packet from a network. The OS recognizes process 0 is not using the CPU and starts running process 1. While the process 1 is running, the I/O completes, moving process 0 back to ready. Finally, process 1 finishes and process 0 runs and then is done. Note that there are many decisions the OS must make, even in the simple example. First, the file system had to decide to run process 1, while process 0 issued an I/O. Doing so improves resource utilization by keeping the CPU busy. Second, the system decided not to switch back to process 0 when its I/O completed. It is not clear if this is a good decision or not. What do you think? This type of decision are made by the OS scheduler. So again, it's the detail of the policy that we discuss and mechanism is that the name of this that schedule the state while the process has been invoked by the CPU through main is named OS scheduler, which we're gonna discuss future. As I said, we will gonna refine this notion as more and more details. So as more and more information we encounter. So the OS is a program, and like any program, it has some key data structures. that track various relevant pieces of information. To track the state of each process, for example, the OS likely will keep some kind of process list for all processes that are ready and some additional information to track which processes is currently running. So again, it's gonna keep this database of that for it to be able to manage that. The OS must also track in some way block processes, so it must have a power to block processes when an IO event completes. The OS should also make sure to wake the correct processes and ready it to run again. So it's kind of like one of this design principles or this characteristic that OS needs to fulfill in order to be able to call OS, because if one program could take over you, you are not qualified as an OS, right? Figure 4.5 show what type of information the OS needs to track about each process in the x86 kernel. Similar process structures exist in operating systems such as Linux, Mac OS X, or Windows. So these are actually a process, right? A process structures rather that tracks the process. So look them up and see how much more complicated they are in the modern world, operating system. So again, we will not be able to understand the current operating system because it's such complex. We can only understand the first operating system or where it starts or the basics of it, right? So from the figure, you can see a couple of important pieces of information the OS tracks about the process. The register context will hold for a stop process. So the register context will hold for a stop process the context of its registers. When a process is stopped, its registers will be saved to this memory location. So when the process is stopped, its registers of that process will save to this memory location. So by restoring this register, like placing their values back into the actual physical register, the OS can resume running the process. So this is how you go back to your pen after you have called from of your boss from your desk. You its register will be saved to its memory location. So it actually physically being saved on that memory location. So by restoring these registers, placing their values of that registers back into this to the actual physical registers, the OS can resume the running process. So this is how you get back the running process. So we'll learn more about this technique known as context switch in future videos. So this is how you context switch in memory. So when you go to this, I don't just activating or switching the instruction of the CPU. I'm literally switching the physical value of the registers of the memory to get into that process. Now, let's understand this code a little bit better. So the registers XB6 will save and restore to stop and subsequently restart a process. So this process structure and the registers of it, one of its power is it actually allow you to stop and subsequently restart that process, which allows concurrency. So the different states a process can be in. So as you can see, there are different states aside from that initial basic running block and ready. You have unused, embryo, sleeping, runnable, running, zombie. And in modern operating system, you can imagine how much more complicated it is. So one of these things that this process structure does is that it has the start of a process memory, the size of the process memory. So again, it's all about the memory. Again, the paging and swapping of this memory is the key in understanding this magic of operating system, right? The virtualizing of memory. The size of process memory, bottom of kernel stack for this process state, process ID, parent process, if 0, sleeping on chan, if not 0, sleeping on chan, if not 0 has been killed. So if it's not 0, it has been killed, and then open files. So what files are open of this process current directory, switch here to run process, trap frame for the current interrupt, the trap frame for the current interrupt. So this is actually how we trap to the kernel as well using this process. So these are the things that we track about the process that allows us to manage it. So we use this information to decide what it can do or not do. So you can or to decide using the OS scheduler, right? How it would be run, when it will be run, etc. So you can also see from the figure that there are some other states a process can be in beyond running, ready, and block. Sometimes the system will have an initial state that the process is in when it is being created. So sometimes the system will also have the initial state that the process is in when it is being loaded. So there's another information as well. Also, a process could be placed in a final state where it has exited but has not yet been cleaned up. So it can also be in a final state where it has been exited but also not yet cleaned up. So in Unix-based system, this is called the zombie state of the process, and see if the just finished process executed successfully. So these things or data about the process are used to see if that executed was successful for us to be able to report that, kind of like a test or a quality check. So usually program returns 0 in Unix-based system when they have accomplished a task successfully and non-zero otherwise. When finished, the parent will make one call, like wait, to wait for the completion of the child, and to also indicate to the OS that it can clean up any relevant. When finished, the parent will make one final call to wait for the completion of the child, and to also indicate that the OS that it can clean up any relevant data structure that referred to the now extinct process. So when it's finished, this process structure that store information about this process could make a final call, such as wait. So again, it's a system call to the OS for the completion of the child, and also to indicate to the OS, to call the OS again, that it can clean up any relevant data structure that referred to now extinct process. So any data structure that it occupies on that virtual memory could now be cleaned up by the OS. So we have introduced the most basic abstraction of the OS, the process. It quite simply viewed as a running program. With this conceptual view in mind, we will now move on to the nitty-gritty, the low-level mechanisms needed to implement processes, and the higher-level policies required to schedule them in the intelligent way. So with this, more intricate understanding, not just a running program of the process, we are now ready to tackle the lower-level mechanism to implement these processes or transformation that is simple, but it's actually have different part, kind of like a code, kind of have a different structure depending on a different state on or way of its execution. By combining mechanisms and policies, we will build our understanding of how an operating system virtualizes the CPU. So simple questions such as virtualizing the CPU requires us to understand this complicated process, and then using a mechanism and policies to understand it in a high level detail. So aside data structure, the process list, operating systems are replaced with various important data structures that we will discuss in these notes. Replete with various important data structures that we will discuss in these notes. The process list, also called the task list, is the first such structure. So this structure, which is the process list or proc x86 proc structure, is actually the first data structure. It's also the one that is cleaned up by the extinct process by the OS after such call of the parent require required. It is one of the simpler ones, but certainly any OS that has the ability to run multiple programs at once will have something akin to this structure in order to keep track of all the running programs in the system. Sometimes people refer to the individual structure that store information about process as a process control block. So this is what I'm saying. So sometimes people refer to individual structure that store this information about the process is called process control block. A fancy way of talking about a C structure or a C code that contains information about each process. So this C structure is just a code as well, right? Again, it's kind of like a process that also contains this complicated task. So about each process, also sometimes called a process descriptor because it describes this process. So the process is the major OS abstraction of a running program. At any so this process is another major OS abstraction. This is how it makes the program magic. It's a large concept of OS about a program. So at any point in time, the process can be described by its states, the contents of memory in its address, so the contents of memory or in its virtual space, the contents of that, the contents of CPU registers, including the program counter and then the stack pointer, among others. Again, the program counter is the registers that point to the next instruction, and the stack pointer is forgot that. Where is that stack pointer? So here, the stack pointer, which we're gonna discuss this in the future videos, and associated frame pointer or FP, SP and FP are used to manage the stack for function parameters, local variables, and return addresses. So this is the stack or a virtual memory of the stack uh, uh, It used to manage the stack for the function parameters, local variables, and return address. So you can see that simple two words has a lot of meaning. So the process stack pointer amount and information about I/O such as including the program counter and stack pointer, which manage the stack during that process execution, which we're gonna have further details in the next chapter, and information about I/O such as open files which can be read or written. So the information about the input or output such as the open files which can be written on the disk currently by this process. So as you can see, this process, again I'm gonna repeat this because it's one of the things that makes this complicated word more complete. At any point in time, the process can be described by its state, the contents of memory in its address space, the contents of CPU registers, including the program counter and stack pointer. So again, the process can be described by its state, the memory basically, or the CPU registers or the CPU part, and information about I/O such as open files and which can be read or written, and also the disk. Basically, what that process can do with the hardware as dictated by the OS, right? Whether it's CPU, memory, and then the disk. So the process API consists of calls programs can make related to processes. So the process API consists of calls programs can make related to processes. So the process API consists of calls programs can make related to processes. So the process API, which this we have discussed the main, right? Where is that? Here. So though we defer discussion of real process API, these are the basics. So these are the things that it can use to call the OS related to it, to run it, to make it, to create it, to wait or to destroy a process, etc. Typically, this includes this creation, destruction, and other useful calls. Processes exist in one of many different processes states, including running, ready to run, and block. Different events like getting scheduled or descheduled or waiting for an IO to complete. So these events like getting scheduled or actually descheduled is actually the one that invoke that IO. So those are the events that we discussed that lets the IO to return back to its running states, whether it's getting the scheduled or scheduled. Transition a process from one of these states to the other. So those are the events, the basics of events. But there is more than that, right? So a process list contains information about all processes in the system. So a process list contains information about all processes in the systems, kind of like the structure. Again, each entry is found in what is sometimes called a process control block, which is really just a structure that or C structure that contains information about the specific processes. So we just get those information from that specific processes.